that you, Victoria?
Yeah, I honestly forgot. Don't show people.
Oh no, that's not mine.
That's yours. Sorry, that cake was like mine though. Sorry, I'm sorry. I did do my own.
No, there's 9 there. See? Right there.
Where's the eye?
Yeah, that's mine. All right, you'll see an acid base on Icebox on Thursday. So, can you do this? Do you think? Is that a very good question, Rosalie?
No, like I completely understand the question, but I just can't, like, there's so many K's that I have to keep track of that I don't know what
Okay, so if you're looking at this one,
But what does it mean?
here's the first question. If you're looking at the pH at 3.26, is that acidic or basic? Acidic, right? So for niacin, can you conclude that that's a weak acid or a weak base? You should say weak acid because we got a pH less than 7. That means you can write an equation, and even if you don't know the structure of niacin, you can signify by saying H9. Okay. Remember that when you see a leading H just tells you acid. That's a good thing to keep in mind. And if you add that to some water, it's going to be aqueous. It's going to dissociate to give you some H3O plus and the anion of niacin. Okay. I'm telling you this is an icebox problem. So then the next question is, where are your numbers?
Well, you have some water.
Pardon? So let's do this. Where does the, you got to figure out on the icebox where to put all this stuff. So where does 0.02 go?
Under H9I.
Yeah, so this goes 0.020. Okay. When you read this thing, this part of it right here, that's at equilibrium. Okay. So initially you got 0 and 0. Then the change rate, you should be able to say this goes down, those two go up. But you don't know how much, right? So you can put in X's if you want, but here's the thing. What can you do with the pH? Figure out the concentration of hydrogen, right? Or in this case, hydronium. So you've got some equations to keep in mind. pH equals negative log of pH plus. You can work that backwards and say negative, or the concentration of H plus equals 10 to the negative pH. You can also say concentration of OH. And there are some other ones that you can use. But for this particular question, that's an okay list of equations. So the next question, what do you do with it? Is that math okay? And where does that number go? That's the next
Bottom middle.
bottom right here. Okay. So then what else can you fill in the chart?
All of it.
So what's the value for x? How about if I put x, and then x, and then x? What's this number? What's this number? And bottom down here, 5.50 times 10 to the negative 4 molar. And since it's all 1-to-1 ratio, same thing over here. How did I know what? This one? Because remember that thing right there, H plus is equal to H3O plus. But in water, you don't have this free H plus floating around. It's actually attached to water to give you hydronium ion. So these two things are the same. And when you solve for this, you could put in H3O plus right there, and it would be fine. Okay, Curtis.
So you always assume that the attached to the.
A lot of times, I'll just leave this out. I really tried not to with this one, this in here, this go around, but a lot of times, just for speed, I'll leave that out and make that just H plus. It's the same thing, at least in terms of how you do the process, but it is important to at least recognize that if you don't have just free H floating around, it's actually bound up with the water like that. So this number becomes 0.0194. We'll go through significant figures.
It'd be 195.
Well, I got 1944.
Huh?
If I went 4 significant figures, I'd run that out.
It's 5.50.
Oh, that'd be 4.
Yeah.
There we go.
That's
So that's 5. Thank you. Good catch. Okay. Now can you find KA?
So in this instance, you're assuming that it's negligible? So that that's the belief that we get.
Right in here, you mean?
Yeah.
So let's try this. What's this answer?
Well, like, I wasn't assuming that it was negligible, so I did the 0.02 minus the, oh wait, you just, never mind. I see what you did. I got the same answer.
So the other one is 1.51. These two are negative.
Okay. So my response would be, since you haven't calculated this yet, you can't assume that that's negligible.
I thought you were assuming it was.
No.
You did.
No, I actually, this would be the point minus the x. If you do this right here, then you could assume that that change is comparatively insignificant. Because if the k is 10 to the negative 5 or smaller, you can ignore that x.
Why are you dividing it by 0.02 again?
No, I'm just doing this to show you that if you went with a negligible, like you,
Oh, okay.
okay, the difference isn't tremendous, but in the absence of knowing that answer, you really can't ignore the x, because you don't know if this is going to work out to be a -5 or smaller. Okay. All right. Questions about that particular problem?
Wouldn't it be 1.55 or 1.56?
I got 1.55 times 10 to the -5. So if you're going two significant figures, then you get 1.6 times 10 to the negative 5. This way, 1.5 times 10 to the negative 5. Okay. Any other questions about that one? All right, problem number next. Yes, problem number next. So, unless you know what the acetate ion is, you can abbreviate that with an AC, so you have sodium acetate and an AC. And what do you know about sodium compounds in terms of solubility? Soluble in water, so this will split apart to give you sodium ions and acetate ions. Okay. Next question. What do you know about sodium with respect to pH? No impacts on pH. Okay, and that's because this is the cation of the strong base NaOH. Okay, and you'll need to remember that the cations of the strong bases don't have any acid-base property. If you put sodium in water, sodium ion in water, stir it up, pH is going to be neutral. Okay, you do need to remember that. Then, when you're looking at the acetate ion, question is, does that react with water? And if you're not sure, add an H to it, so you think about it as acetic acid. Is that a strong acid or a weak acid? Weak. Okay. This anion you'll need to remember that it's the anion of a weak acid. This is an important concept, at least for this particular problem, that the anions of weak acids act as bases. Okay. So, in this case, you ignore the sodium, you focus on the acetate ion. All right, water is HOH. What comes out? What are the products? Pardon?
Acetic acid and OH.
Yeah, you need to know how to write this. So your question simply is, what does the acetate react with? Nick, you said hydroxide ion is one of the outputs. Yeah.
And then acetic acid.
And then you get acetic acid. Okay. And that's going to be aqueous as well. So the acetate ion reacts with the hydrogen. And think about, you want to think about the, I got red. You want to think about water as being a positive and a negative. Can you see the purple?
Mm-hmm.
Yes. Okay, I've got a
Kind of.
purple pen up here. I don't know.
No.
Yeah, not
All right. Christina probably not.
really.
I can't
know,
see it.
and I have.
It's,
What's the exact
it's purple.
state?
Anyway, you want to think about water as, acidic hydrogen is a proton is positive and hydroxide is negative. So you answer the question, what does the acetate react with? It reacts with the hydrogen to give you these two things. Okay. The rest of this is an icebox problem. But the first part you got to figure out is how to make the reaction. And there's one more little step that's in here. So your question is, next, where's that 0.2 go?
Acetic acid.
Under the acetic acid.
Acetate or the acetic acid?
Or sorry, acetate.
Acetate. Okay. So that's 0.200. This one's going to be 0, as is the hydroxide. Okay. Are y'all good with this being a basic reaction? Okay, so I'm just going to write up here. Basic reaction. And if it's a basic reaction, do you need Ka or Kb? Gotta have Kb. You have Kb. You figure out Kb.
Yeah.
Remember, in addition to those other equations, Ka times Kb equals Kw, and Kw equals 1 times 10 to the negative 14. You should get 5.56 times 10 to the negative 10.
Which we don't need, or we can ignore it,
So then, this is the question about the x's. You should be able to say this goes down by some amount x, up, and this goes up by some amount x. And because this number is a negative 10, Nick's asking, can you ignore this one? And the answer is yes. Okay, so I'm going to freeze that. Actually, solve for x. Anybody got an answer yet? Like that? Okay. Do you have any questions to this point? So, how do you get pH? That's the next thing.
Negative log.
Okay?
And then
So you can go POH equals negative log. That's a molar. And that number is going to be. Christina, do you have that?
Yeah, 4.97.
Okay. So pH is equal to. Is that acidic or basic?
Basic.
Basic. Okay. Do you have questions about that one? Back.
Not necessarily related to this, but on your other page with the sodium acetate, yeah, maybe I was just confused, but I thought that a metal with a non-metal would fully react. Like it wouldn't have, so it does, so what, I guess like this is like going way back to like the first equilibrium
So
stuff.
this is like, okay, so downstairs in the vault, we've got, there's a bucket of sodium acetate. If I were to bring it, it's just a white solid, it looks like table salt for all intents and purposes. I could, if I brought it out and said, hey, Becca, make this solution, and you mass it out, and then you dumped it in, and you stirred it up, this would be the pH of the resulting solution.
And so even though you drew the equilibrium lines, we can assume that it went completely to.
Yeah, let's get rid of the bottom one.
Okay, that was my only confusion. I was like, wait.
This one, equilibrium one, so.
Okay.
Okay. Other questions about this one? Either calculation-wise, icebox.
Should we expect the question on Thursday to look more like this one or more like the other one?
Yes. I mean, either one is, I'd say either one is fair game. They're both, I mean, they both involve ice boxes. I haven't put Thursdays together yet. You're getting last week's back tonight, so you take, you'll be able to take a look at it. But either one of these would be fair game. They're both, they're similar. I mean, you've got similar, I don't know, it's, yeah. Yes. Other questions? Yeah, right on. Good. I don't have specifically one like this, but if you go to the file section, there's somewhere in the 122 files that I dumped in there. There's some stuff like this somewhere. To be honest, you'd have to go search for it. I don't remember a specific one that is just this. But there's a little bit of everything in there that covers topics, knowledge and calculations, pH, POH manipulations. There's some in there that deal with this kind of stuff over here. So, my suggestion would be to go in and take a look, and if there's some that, like, oh yeah, you can try this. If you look at it and you're solid. Yeah. Okay. Do you feel okay with those things? Sort of. Okay. All right, I just got a few more things on this particular set of slides, and then I'll finish out 14 with a different one. So I've got to do some recombining. Here you go. This reaction is one I just went through. And it would be a good thing for y'all to remember that these are not just all anions, but they're the anions of the weak bases. So anything like the sodium acetate, if you had a nitrite, not the nitrate, but if you had a nitrite, the nitrite's going to be the weak, or the anion of the weak base. If you had the niacin anion, benzoate anion, anything that is not the anion of a strong acid will do this in water.
Can you repeat the whole chapter?
Yes, anything that is the anion of a weak acid will undergo this reaction in water. So you dump it in that anion, and like on my example, this is up here. I'll come back to this. But on this example, where I wrote water as HOH, there's the anion reacts with water to give you the weak acid and then the OH. Generically speaking, that's this thing right here. You could so like on here with the acetate, you could put in here benzoate or any other anion from the weak acid. And the same reaction happens.
So on the test, you're gonna want us to be able to write that equation.
Yeah, I mean that's what you'd have to do for a problem like this one. So Holly's asking, is there going to be one like this or this? And sure. I mean, like I said, I haven't sat down to write this thing yet. That's tonight, tomorrow.
So how do we know?
So you're paying attention to like in the cover of this.
So the bottom one.
Let me go to this one. But like this one, you're looking at. You got to keep in mind sodium doesn't react with water, so there's no acid-base impact. The acetate is associated with the weak acid, sodium acid, or acetic acid. That will react with water like this. So you should be able to say, recognize that it's the anion of a weak acid, write this reaction. You should be able to do that. Okay.
Would always be basic.
So like if I said, for instance, this compound, or this particular ion, sodium benzoate, or potassium benzoate, sodium benzoate, is used to, as a preservative. Okay. There is also the compound benzoic acid. Okay. If you dissolve potassium benzoate in water, first question, what do you associate potassium with respect to acids and bases? Or another way to think about that, take the potassium, put an OH on it. Is that a strong acid or a strong base or a weak base? Strong. Strong bases are group 1 hydroxides and then heavy group 2. So this, as a strong base, means that the potassium has no impacts acid base.
So we don't have to worry about it.
So you don't have to worry about it.
And so then,
Okay. So that means you've got this benzoate anion, and you don't even need to know the structure of this. To be honest, it's not important for this kind of a problem. You need to recognize that in an acid-base question, that is going to be so the anion of a weak acid, and then the benzoic acid is it. So H-ben. And then if you're writing the equation, benzoate ion reacts with water, and I'll write it as HOH. What's produced? Back to benzoic acid and OH minus. Okay. Then you're asking the question, is that acidic or basic? It's a basic reaction, which means you need KB. Somewhere on a table, pardon? Yeah, that leading H tells you that this is an acid, but in terms of this reaction, as it goes this direction, it's a basic reaction. Okay. Ka is written down somewhere, then you need to remember the Ka times Kb is going to. Okay, fine.
Like in a solution of benzoic acid, or I guess sodium benzoate, whatever, like both reactions are occurring, right? To some extent or another. But one predominates over the other, right? It's going to be part of it. So why do we even bother with, like, I'm guessing in this case, like the second equation doesn't happen significantly. I don't know.
Like you're going backwards one?
Well, the benzoate to benzoic acid. I'm guessing it's more benzoic than benzoic acid in solution.
You have to look at the Kb numbers.
Right, but then what's the point of calculating the pOH of something that's not even real? Like, you know what I'm saying? Like, you'll never isolate that. You know?
No, you won't, but like, for instance, same kind of thing I was telling, I guess, Becca, if I just gave you some sodium benzoate or potassium benzoate and said, here, take the solid, put it in water, stir it up, now measure the pH. If you know the concentration of the solution that you made, like that, you'd find that a solution of some benzoate salt dissolved in water is going to be a pH greater than 7. It's going to be basic.
Okay.
Because it will react with water in this fashion.
Okay. So if you don't start with the acid,
Right.
it won't form itself. I guess that's what I was. It might sound weird. Actually, it did sound weird, but I mean, like if it's a stronger acid, it'll exist in that form, right?
If it's a stronger acid, you'd find that the equilibrium will probably shift to the left. I mean, if you're just looking at which one. Right. Okay. But if you're like this, if you start out with, and then I guess here's the way I'd answer your question. If you start out icebox wise and come back down here, looks like that. if you start out with this and you're gonna make a solution, say 0.2 molar, that's going to be the 0 and that's going to be 0. So as that dissolves then, this has to go down, these have to go up by some amount.
Okay.
And then once the solution hits an equilibrium, the equilibrium can lie to one side or the other, whatever.
It'll just be super small.
But once you know this number, you can get POH, which you can convert to pH. Yeah.
Okay.
Yeah. Okay. Rosalie.
How do we know which direction the equation needs to be based on the question?
So for this one, either of these two, you're starting with the anion, which is that.
So we just assume that we're going to the acid?
That when it reacts with water, it pulls off the hydrogen, you get the acid and then hydroxide. Okay. If you have a problem like this one, where you're told, like, you don't know the structure of niacin and that's fine, but if you're told that the pH is less than 7, that tells you that it's an acid,
Okay,
right?
yeah.
And in that case, that's why I wrote this as H9. I mean, the structure for niacins is a 8 carbon, whatever. But you don't need to know the structure. All you need to know is that it's acidic. So it's the way I abbreviate it.
Okay.
That tells you that your reaction looks like this. If it's the anion, then you're writing them.
Anion, or
Yeah.
base to acid versus acid. Okay.
Okay. All right. Good questions. Any others before I finish out? All right. Let's go here. Here you go. I don't put these in with icebox questions, but they're worth understanding, at least in terms of what happens. There are a lot of metals that when you dump them into water, the metal ions, they form this hydrated structure, and then they can interact with water to produce hydronium. Okay. So certain, metal cations, you look at a transition metals, metal cations will react with water to produce an acidic solution. Okay. I won't ask you to do things like draw this out, but you need to at least conceptually keep in mind metal cations react with water to produce an acidic solution. Okay. I'll leave these two here. Is that okay, that statement?
What does it mean by acidic?
So remember the Arrhenius definition? Okay, Arrhenius definition says that an acid is something that increases the concentration of hydrogen ion in solution.
Okay, yeah.
So something like NH4 can lose, it can give up its hydrogen, and that would be called the acidic proton. Same thing like hydrochloric acid, HCl, can give up the hydrogen, and that would be considered the acidic proton. It's another way to say.
Don't you assume that an acid has an H that it gives up?
For the definitions to right now, yes. Because there's another definition of acid.
No.
Yes.
And when it says lower, it means make more acidic.
Yeah, because remember pH less than 7 is acidic. Fine.
The solvation, are those actual bonds to the metal, or are they just sort of surrounding it?
Yeah, I think your book describes these as covalent bonds between the metal ion and the water, but there's no. I would disagree with your book on this part. We go here real fast. like iron 3 plus, and then water. Remember that water's highly polar, so you got a big negative component to that side. There's no sharing of electrons here, but you do get the attraction between the cation and this really negative aspect, or partial negative charge that sits on one wall.
So it's like closer to an ionic thing.
Yeah, like an ion dipole interaction. It's a real strong ion dipole interaction, and it's enough in the hydrated form when you get 6 waters around it that losing that hydrogen right there actually gets stabilized by this entire structure. So that's, I mean, and that's what you're looking at over here. That gets lost. That lost hydrogen allows for a bond to form here, and you've got this big structure that stabilizes everything else. So, yeah. All right, next slide looks like this. You probably will not see questions that ask you this kind of thing. Okay. But again, and this, like what Mike was asking about, that lost, and so, and Rosalie, this is your acidic proton. That lost acidic proton forms hydronium, and then that's stabilized by this larger structure. You'll notice the charge changes. More acidic, pH less than 7. The next slide, though, you want to pay attention to the chart that shows up. Okay. The chart's going to be probably more important than what it says here. The writers finished. Charges over here, pay attention to this statement. Do you remember back from I think it was 61, the whole thing about electron shielding? Okay, that when you got a bunch of electrons in between the outer shell and the nucleus, there's some shielding involved. Okay, if you don't remember that, you might want to take a look at it. When you're looking at something like aluminum, which is small, versus something like iron and zinc, which are much larger, these have got more shielding between the nucleus and the outer shell. Aluminum's got a much greater attraction for electrons because there's less shielding. This number tells you the likelihood that it will strip off the hydroxide and kick out the hydrogen. So back to this one. You got a smaller atom, larger charge, more likely to move this reaction forward. That's what this is telling you. Okay. So larger charge, so like aluminum 3 plus, there's iron 3 plus, iron 2 plus. The iron 3 plus has got a larger charge, it's got a stronger Ka. When you're looking at the size of the atom, that's also going to play a role as well. Okay. So keep that in mind. Rosalie.
So you said the smaller atom with the larger charge is more likely to strip the electrons off?
In terms of, so think about this reaction right here, where that metal is going to interact with water. Okay. And then as it does that, it kicks out the hydrogen to form hydronium. Smaller atoms are going to, that'll happen more likely with them. And charges, iron 3 versus iron 2, the larger the charge, the more likely that is to happen.
More likely it is to kick out the H.
Yeah. So if I draw a couple of these without those big hydrated structures. So by writing without doing the big hydrated structures, you're looking at something like this. And for this one, you're going to get FeOH. And that's going to be 1 plus and H3 plus. Okay. So you could be asking a couple of questions, like in comparing these two, which one's going to sit more to the right? Reaction 1 or reaction 2?
Reaction 1.
Reaction 1. Okay. If you compare the KAs, larger Ka, smaller Ka. Larger Ka means reaction further to the right. Which one's going to have a lower pH?
Reaction
1.
Reaction 1. Because if it lies more to the right, that means you got a greater concentration of hydronium, which means lower pH. Okay. You had iron 3 plus up here doing the same thing. I think that number was. So of these three, 1, 2, or 3, looking at the Ka values, which one's the strongest acid from that point of view?
3.
3. Okay. Largest Ka value, which means further to the right, lower pH. This one's going to be the weakest. Okay. Does that reaction occur?
No.
Okay. That was just my check. See whether they were paying attention.
Well, that's like check time. But you know, now we're only.
So
gonna
Rosalie, over
find
the
out
course of the year, how many times have I said significant figures matter?
I think you say it like every class,
Yes.
multiple times in class.
Exhaust myself.
And do we do significant figures?
We'll talk about that when I give your test. How many
Like
times
this
do I say?
specifically?
How many times do I say labels matter? Put your labels down.
So many.
A couple times. At least once or twice. Like the dumb kid today in class said, phones away, Chromebooks away. As soon as I say, now start working on this, earbuds go in, Chromebook comes up. I'm like, you're stupid. Yeah, and then the kid went in, I'm like, dude, quit watching videos. And after I oh, I'm so sorry, Mr. Davis, I was watching videos, I won't do that again. Please don't tell my dad. That's whose dad's getting an email. Idiot child. Yeah, that's what I deal with. I mean, because like, and then the kid comes, this kills me, because then the kid comes in later and he's like, can I get some help? Seriously? You're asking me for help? You're stupid.
Why? He asked you for help.
Because he sits in class and he tries to do earbuds and Chromebook and videos. And I'm like, no, you can't come in for help. I'm friends with his mom. I'm like, hey, you're a kid. Have a conversation with him, please. He lost his phone for 2 days. Okay, on day 3, he's back in with his phone. I wonder why the kid's not doing well. Whatever. Okay. High school, for all you high schoolers in here, I mean, you're fine. This is not all of them. This is the occasional one. Down at the bottom, this is to show you what these look like with different acid-base indicators. So the sodium nitrate, neutral pH is 7, and I don't know, read these numbers.
6.9, 5.5, 3.5.
So calcium nitrate, calcium's just a little bit. Then you got the zinc. The nitrate part doesn't react with water, but the zinc does. It drops the pH down to 5.5. And then the aluminum down at the end is a pH of 3.5. Okay. Just to show you that the different cations will have impacts on acid-base character, whereas the anions, like the nitrates, do not. Okay. Like an anion that does? Yeah, like ones that, these, so when you're looking at anions that do impact acid and base, you're looking at stuff like, not that one, specific. Benzoate, nitrite, sulfite, phosphite. Those are all the anions and weak acids. And if you react any of these with water, you're going to get, I'm just going to write this way, HX plus OH minus. In every case where this is the X. Okay. So the anions, and again, these are the anions and weak acids. They'll react with water to give you a basic solution. Okay. All right. Last couple slides will take a break. This one. Leave that on there for a minute. You want to get the third statement down. Nope, not yet.
Was that PO3 or PO4 that you had on the paper for number 2?
Oh, PO3. Yeah, phosphorus acid.
Whereas like for number 1, if you have PO4, SO4, and a 3, it would not affect?
Even phosphoric acid, H3PO4, is considered a weak acid.
Oh.
But this, for up here, the anions that I put up, these are all ites. So nitrite, sulfite, phosphite. I just kept the ite grouping is all.
But like,
But if you have nitrate, NO3, that's strong. Sulfate, SO4, that's strong.
and so it won't affect.
Right. So flip this. And then Mike statement 6 is what you were asking about. Ready? Almost. Oh,
You're gonna be behind there soon.
all right, here we go. Oh, let's see.
Can we see an equation for number 6?
For number 6.
Yeah, so what is solution to change? Like,
So-
or what that would consist
If
of?
you were looking at this, if you're looking at something like like, you have a solution made up of benzoate ion and the acid, benzoic acid. The question about whether it's a stronger acid or a stronger base is answered by the values for Ka and Kb. And I don't know what those numbers are, but for the sake of illustration, say this was 6.7 times 10 to the negative 5, this is going to be, I don't know, times 10 to the negative 9 or 10. That would tell you that it's a stronger acid than the benzoate ion is a base. Okay.
Where's the entire solution? Is like one
Just if you're just evaluating, and this is, if you're given a situation like this question, where you're starting out with, I mean, there is no acetic acid in there, there's no hydroxide, you're making that solution originally, these are zeros, then this reaction will proceed to the right, okay? If you're asking the question, like in this case, is the Ka right up here, is acetic acid a stronger acid than acetate is a base? The answer is yes. This is a stronger acid than this is a base. Because they got a bigger K value. So if you're looking into two equations, this would sit further to the right than that one does. Okay. But in this particular situation, in making the solution, there is no acid, there's no base to start out. So those are zeros. And then as the reaction proceeds, this has to go to the right, this has to go down, these two have to go up. Okay. And that's where you do the rest of this. But in answer to the question, which is it a stronger acid or a stronger base, the salt or the acid, you've got to pay attention to these two numbers. And that's what 6 is telling
As
you.
in, like, if we're talking about acetate, is it stronger as a base or stronger as an acid, correct? Or,
If it's got, like, sorry, in this case, if you have a solution that has both in it, like I take acetic acid and sodium acetate,
yeah,
and I go,
yes.
okay, the pH of that will depend on the Ka and Kb values. You have to do calculation. We'll get to that. If not tonight, I'll do it on Thursday. But you can do a calculation to figure out the pH, and it's a ratio between the base part, which is the acetate, and the acid part, which is the acetic acid. Okay. And that ratio will, this is the Ka lab that y'all did, the half titration. That's what this is. Okay. Okay.
Thanks.
I think you just answered it, but so, like, what it's, like, number 2 was an anion is a conjugate base of weak acid. It's talking about that as, like, by itself. Like, if you put acetic acid in water, you're gonna get the conjugate base out of it, but that's not important because the acid is stronger.
Right.
It's talking about if you just take
The base.
sodium acetate or whatever,
Throw it in water.
it will affect it.
pH goes up. Yeah. Okay, so then the next couple slides, I'm trying to do this quickly. For this one, even though the electronegativity difference is greater here with the HF compared to the HCl, think about numbers of electrons. Which one's going to have the largest London dispersion force, the HF or the HBr? HBr. You've got 35 electrons on the bromine down here to deal with, but you've only got 9 on the fluorine. Okay? So in terms of the polarity, or like this one up here, okay, that's going to be more polar. It's because of that extra batch of electrons, stronger acid. HF is actually a weak acid. Sure.
Is there a reason why it doesn't follow the trend of hydrogen chloride, hydrogen bromide, hydrogen iodine?
Oh, you can put hydrogen iodide down here, and it'd be stronger. I don't know what the K is going to be much greater than 1.
But is there a reason?
Increase.
Sorry.
No, I was going to say, it increases as you go down.
So we more polar.
Yeah, because iodine's got 53 electrons around it that can be, off on one side at any given point in time, makes it even more polar. So, is that?
Well, I was just wondering why hydrogen fluoride is a weak acid and it doesn't follow the trend of chlorine, bromine, and iodine.
What trend is that?
Well,
So, I mean, as you go top to bottom, the acids get stronger. So, weakest HI would be the strongest. That is the trend that you're looking at. And this one in particular is going, like, fluorine, because it's got a real high electronegativity, actually has a pretty tight hold on that proton that's sitting there. And remember that it's also small, size-wise. So there's a fairly tight hold on that proton. For these two, you've got much larger atoms or ions, so they're gonna have a little bit weaker hold. They've also got some shielding that's going to prevent some interactions. More likely to lose their proton. Okay. Iodine's gonna be even stronger. Rosemary.
So, okay, so if it's a super polar compound between H and X, then it's gonna be acidic. More
And
acidic.
strong.
And if it's a weak bond between H and X, then it's gonna be acidic.
So the greater the polarity, if you want to think about it that way, the more acidic it is.
Yeah,
Okay.
so I can just cross out the weaker part.
Yeah, you can do that. For these ones, so there are a couple things on oxyacids, and I'll get through these quickly, and then we're going to go to the Lewis acid, the last definition. For Rosalind, we'll take a break. For these ones, you're looking at the strength of the acid based on the electronegativity of whatever the non-metal is. Okay. So if you think back to, all got the periodic table with electronegativity values on the back. Chlorine's 3.16, a little higher than that. Bromine's a little higher. I need to change these numbers. Those are not right. Anyway, more electronegative, less electronegative, more acidic, less acidic. And if you look at the Kas, the same thing. -8 to -14. So more electronegative non-metal is going to give you a stronger acid. Okay. That said,
can you repeat that real quick?
yeah, more electronegative non-metal gives you a stronger acid. And it has to do with, remember electronegativity is the pull that an atom has for electrons?
Totally.
So when you do that, it's going to pull electrons more toward it, which leaves that hydrogen exposed and more likely to poof, go off.
So like fluorine.
Pardon?
It's like fluorine.
Yeah, and so fluorine, like HF, if you put this on here, but it's not, HF's not an oxyacid, of course, but if you put that up here, more electronegativity, the Ka is a -4. 6.8 times 10 to the -4. So it's a stronger weak acid. Okay. You should recognize that all these are weak acids, right? Okay. Let's go to the next slide.
So,
Yeah, go ahead.
an oxy.
So oxyacid contains, take a wild guess.
Oxygen?
Oxygen.
That's it, that's all.
That's it, oxyacids.
Okay.
Next slide, oxyacids. More oxygens makes them stronger acids. And the reason on this one also gets down to the fact that when you take that hydrogen away, it leaves a negative charge out here. Think back to resonance. You guys remember resonance from 160 to whatever? Okay. More oxygens allow for resonance and it stabilizes the anion. So, more oxygens, stronger acid. Less oxygens, weaker acid. Okay. And put that there, I've already said that. Any questions on that one? Jack?
So, in other words, it's the ability for the compounds to release the hydrogen that
Yeah.
makes it stronger.
Yeah. And the next one up here, this is your resonance, that double bond, you just kind of think about it as flipping back and forth. As that occurs, that negative charge gets stabilized on the end of the molecule. You think about it being distributed. So it doesn't just sit on one oxygen, but it sits kind of on both. But that resonance happens so fast that it's like a half negative and a half negative, half negative, half negative. And when you're looking at structures like this, if you've got a negative here, you can only resonate once. Here you get two others. Here you get resonating around the whole thing. So when that happens, you get more stability, less stability. For the carbonic acids, as these are called, you get more stability when they can resonate. All right, last one. The last definition for acids and bases you'll need to know are the Lewis acids and bases. And you'll notice that they do not talk about hydrogen. Okay. Acids will accept electron pairs. I'm cheating a little bit on here. So let's go here. So when you're looking at those cations from a while back, do you classify those as Lewis acids or Lewis bases? Okay, so ready, go back to the definition. Lewis acids accept electron pairs. What's the aluminum doing?
Accepting.
Accepts it.
Yeah. So those metals can be classified, in this case, as a Lewis acid. When you're looking at, I'll leave this here for just a moment, you want to write this down, this would be at least in this sense, a Lewis acid. This,
As in aluminum is a Lewis acid.
yeah. And that's because it accepts the electron pair. Okay. Lewis bases, this is on the last slide, donate electron pairs.
Does that mean that hydrogen can't be a Lewis acid since it can't accept an
So if I
electron
have hydrogen
pair?
ion,
Yeah.
and I react that with, say, I don't know, NO2, it's got an extra pair of electrons on there. What does that do?
So you'd have two of those then, right? Or well, I guess, yeah, okay. So even though it says like able to accept electron pairs, it's not necessarily that
Pairs.
pair.
Can you go back to what you said?
Yeah. Okay. And it opens up a whole bunch of, a whole different world for acids and bases. And for people who do, in particular, organic chemistry, you can do a lot of crazy stuff with different kinds of acids and bases that are not centered on hydrogen and hydroxide. So, Arrhenius, you got, that's hydrogen and hydroxide. Bronsted-Lowry talks about proton accepting, proton donating. Lewis acids are ones that accept the electron pair. In this case, the boron has an empty spot. It's only got 6 valence electrons here. That would fill the octet, so now you count them up, you've got 8 and 8. The ammonia has an electron pair to donate. So the bases are going to be electron pair donators. Okay. And remember that the Bronsted-Lowry bases are ones that accept protons. So that's this last statement, that if it fits into that category of accepting protons, that means it has extra electrons that can be donated. Okay.
Vice versa.
Pardon?
All Lewis bases and Bronsted-Lowry bases.
Yeah.
So you're saying all front?
If you can consider, so Bronsted-Lowry bases can accept a proton. And the reason they can accept a proton is because they've got an electron pair sitting out there to form that bond. because remember the proton's just, it's a bare proton, positive charge, electron pair, and then they'll stick. Okay. So that's where your Bronson-Lowry definition of a base matches up with the Lewis acid.
But
and
the,
the Lewis base.
but a Bronson-Lowry acid doesn't work the same way as a
No,
Lewis
because
acid.
Bronson-Lowry acids are compounds that donate hydrogens. Okay. So the Arrhenius definition and the Bronson-Lowry definition for bases are essentially the same. Arrhenius, increased hydrogen concentration. Bronsted-Lowry donates proton. Lewis definition for acids accepts the electron pair. Bases donate the electron pair. Okay. All right, and I think that's it. And that's not the end of chapter 14, but it's the end of what I have for chapter 14 on this particular set of slides. So let's take a break. Come back, I'll give you one more icebox problem, then I'll do it with your talk about your tests. Okay.